Hi, in today's episode, we will discuss linear regression. We will implement it in Python and explore its applications. Let's get started. First, let's explain what linear regression is. It's a brief statistical method used to model the relationship between one or more independent variables, denoted by x. The goal is to find functions that best fit a set of points in space, so the sum of squared distances between these points and the points predicted by this function is small as possible. Now, in simple terms, let's consider a two-dimensional plane where the x-axis represents independent variable and the y-axis represents the dependent variable. We can imagine a set of points scattered on this plane. Although they aren't arranged in any rigid pattern, you can observe a certain trend. We can intuitively draw a straight line that shows this trend, approximately fitting through the middle of the set of points. But let's take a step back and ask, what is the purpose of this fitting line? The answer is quite simple. It's used to make prediction based on new x data for which we don't know y values. An example for this would be estimating the amount of staff needed in the company, y value, based on the number of customer order, x value. Like our predictive models, linear regression has an error margin. This error can be larger or smaller, depending on the nature of the phenomenon being predicted. To make accurate predictions, we first need to properly determine a function. We can't do this based on intuition, but rather on the specific condition. We will consider the best fit to be the one where the sum of distances of the actual points from the points predicted by the mentioned function is the smallest. When I mention distances, I actually mean the prediction error of y value for each point, which we use to make the fit. In our two-dimensional case, the function we are looking for takes the form of a linear function, y equals a times x plus b. The coefficient a determines the slope of the line. The value of this function at the specific point of our set is generally different from the actual position of that point on the y-axis. This difference is the error we want to sum up across the all data and then minimize. We won't go through all mathematical transformation, but we will note their assumptions. For the fitting function f, we can write its total error as by summing the differences between y values of the point and their predictions. Each of these differences can be positive or negative, since the points might lie below or above the function f. We want to know for which value of a and b the sum of the absolute values without sign is the smallest. Therefore, S will be the sum of squared error, ensuring that for each point we add positive values and they don't cancel each other out. The condition for the minimum value of the function s, which depends on the parameters a and b, is setting the partial derivatives s with respect a and s with respect b to 0. This gives us a system of two equations with two unknowns. Solving this essentially simple mathematical problem gives us the formulas for what a and b should be. These formulas, although they look somewhat intimidating at the first glance, involve simple operations like addition, multiplication, and squaring. All the necessary input data is provided as a series of points with x and y coordinates. In Python, it looks much friendlier. Before we move on to the Python code, it's worth mentioning that the fitting function f can predict values based on the larger number of independent variables, such as x, y, z. In such case, we solve a larger system of equations to find more coefficients a, b, c, and d. Let's start by preparing the show plot function that will plot the points with x and y coordinates and the fitting line created based on the parameters a and b. We will use matplotlib library to assign the figure and axis object to our plot variables. Then we will create a list of predicted y values based on the fitting parameters. Using the axis object, we will plot two graphs, one with the original points and another with the line draw using y values delivered from the line fit of a times x plus b. In the next step, we will label the axis, add a title, and show the legend on the plot. We will return the fig and ax objects in the last line. This will be useful later. Moving on to the core linear regression model, we will create a linear regression function that will take two lists of points coordinates, x and y, and then return the coefficient of the fitting line. In this example, we will limit ourselves to two-dimensional space, and at the very beginning, we will ensure that the x and y list have the same length, meaning that all points have the both coordinates. Here we calculate the parameters of our linear function and implement the seemingly complex formula for a and b that we saw earlier. In practice, it consists of simple components that we calculate and store in separate variables. These include the total number of points, the sum of the x coordinates, the sum of the y coordinates, the sum of the product of x and y coordinates for all points, the sum of squared x coordinates. Next, we substitute the appropriate components into the formula and get the values of a and b. For a set of sample data, we obtain the fitting coefficient. Using the previously prepared function, we get the plot where the dots represent the data to which we fitted the line visible on the graph. In practice, we don't have to reinvent the wheel. Linear regression is available in ready-to-use libraries. Probably the most popular and well-documented library is scikit-learn. The easiest way to install it is to use pip package manager with this command. More information can be found at official website. I already have the scikit-learn package installed in my environment. Let's import the linear regression model and prepare sample data. These are the same data as in the previous example. The difference is that the linear regression model expects the independent variables in the slightly different format, as it is designed to operate in higher dimensional space, or in other words, with more independent variables. In our case, we have only the x-axis as an independent variable, so for each point we provide a single element list. With this data, all we need to do is to create the model and use the fit method to fit it to the given points. We can easily access the coefficients of the fitted line. As you can see, the coefficients are the same as in the previous example. And with a slight modification of the XList format, we can present these points using the prepared showPlot function. Having the trained model, we can make prediction using the predict method on new data. We will use the showPlot function again and finally make use of this returned axis object to plot the new predicted data on the graph. That's it for today's topic on linear regression. We have learned about the concept behind it and ready-to-use tool in the form of scikit-learn library. The library, of course, offers much more and deserves an entire series of videos. It will definitely appear again on this channel. But for now, thank you for your attention and see you in the next video.